Welcome to the 5th video in the series on rational functions. This will be the final video in this series, and this video will conclude with a graph of a rational function which has a slant asymptote. In the interest of time, I've already started some of the steps. Some of the videos in the series were a little bit lengthy. In this video, I wanted to keep it a little bit shorter. So I've already started a couple of steps. And if you haven't seen any of my videos in the series on graphing rational functions, please feel free to check those out. So, as I had done in my other videos, the first step in this is how I do it. What I like to do first is I like to determine whether we have a horizontal or a slant asymptote. And if you had missed that, I covered this in video 2. And basically what you're doing is you're looking for the degree of the numerator and the degree of the denominator, and that's the highest exponent in each. And that's going to tell you whether you have a horizontal or a slant asymptote. So if I look at the degree of the numerator here, the degree of the numerator is going to wind up being a 3, and the degree of the denominator is going to be a 2. So if you recall from video number 2, if the numerator's degree was larger than the denominator's degree, this would tell us that we're going to have a slant asymptote. All right, and then what we did was to actually find the slant asymptote itself, we wound up dividing the rational function out. And, depending on the function, sometimes you can use synthetic division. In this case, we're going to wind up using long division. And like I said, in the interest of time, I've already done some of that out. And if you need a little bit more of a detailed approach on long division, I do cover a lot of that in video number 2. So basically, the approach was for long division, what you're looking for is the lead term in your divisor and the lead term of your dividend. And what you need is, since I have x cubed over here in my dividend, I need to also have x cubed under here. So what times x squared will give me x cubed? And the answer was x. So then what I did was I took the x and I multiplied it times all 3 of these. And I got all 3 of these values. You can see it here. And the original signs for each are in the highlighted part in yellow. And then if you remember, after you do the multiplication, you have to change all the signs. So that's what you see here in green. Those are the signs that were changed after I'd subtracted. And then what was left was 2x squared plus 7x plus 3. I brought down to 3. And then again, my lead term under here was 2x squared. So I needed to come over here to the lead term and say, well, what times x squared would give me 2x squared? And then the answer was 2. So then I multiplied the 2 times all 3 of these terms, and that's how I got this polynomial down here. And then here's your remainder. But it was, again, as I mentioned in video number 2, you're not really interested or concerned about the remainder for your slant asymptote. All you really care about is this part up top here. All you really need is the quotient, and that's going to give you the line for your slant asymptote. So I'm going to come back over here, and we're going to write that in. So my slant asymptote is going to be the line y equals x plus 2. All right, and then the second step would be to factor this. So as you can see in this function here, I've got 4 terms in my numerator. So when I see 4 terms, I'm thinking, possibly factoring by grouping. And again, I've already taken the liberty to do that work. If I come over here, again, I have 4 terms in the numerator. And I factored that by grouping. What I wound up doing was, you can see I wound up grouping the first 2 terms and then the second 2 terms. And then I wound up taking a greatest common factor of x squared out of this first parenthesis. I was left with x plus 3. And then in the second grouping, I just had 1 times x plus 3. And then I saw in the numerator again, I could factor out a common factor of x plus 3, which is what I have down here. And then when I did that, all I had left was x squared plus 1. So when I factored out the x plus 3, I was left with x squared plus 1. And then the denominator, that was only a trinomial, so that winds up factoring into, as you can see, x plus 3 times x minus 2. And that's what I would have had over here. This should be x plus 3 times x minus 2. And I'm going to bring that over here now. So that's going to be my factored function here. So we have the new factorization. It's going to be x squared plus 1 times x plus 3. And then we have x plus 3 in the denominator times x minus 2. And if you remember from step 2, what we're going to do is after we factor it, we're going to look to see if we have any, if we can cancel any factors. I can cancel the x plus 3's. And again, when we have those canceled factors, that is what's telling us we have a presence of a hole there. And then we're actually going to find the coordinates of the hole in the next step, step 3. And we're going to use that canceled factor of x plus 3 to help us figure out the coordinates of the hole. So that's the first 2 steps of my approach. I'm going to be right back with step 3, where we determine the vertical asymptote, the holes, and in the presence of the x and y intercepts. I'm just going to clean this up a little bit. I'm going to sketch in the horizontal or the slant asymptote, and I will be right back with the rest of the steps. All right, welcome back. So on the graph, you can see I have the slant asymptote drawn out. And now we're going to continue with step 3. And you can see I have the reduced function here, x squared plus 1 over x minus 2. So from now on, throughout the rest of the example, we're going to wind up working with the reduced function. So in step 3, what I like to do is I like to find my vertical asymptote. And to find the vertical asymptote, what we're going to do is we're only going to use the remaining factors in the denominator to determine where that vertical asymptote would be. So I have x minus 2 as my remaining factor, and we're just going to set that equal to 0, and we're going to solve. So we're going to have a vertical asymptote at x equals 2, and I'm going to put that on the graph. So we have this right here, and that'll give us our, nice guideline to work with when we start doing our test points and our test regions. And the next thing we're going to do is the hole in the graph. We've already determined that we did have a hole in the graph. So again, the holes are created by canceled factors, and we cancel the factor of x plus 3. So all we're going to do is use that canceled factor, set that equal to 0, and we're going to have our, remember the hole, we need an x and a y coordinate. So the x coordinate of the hole would be -3. And then all we need to do is substitute this value of -3 into the reduced function to figure out the y coordinate. So I'm just going to move this up just a little bit, and I still have the function there. So to find the y coordinate, or the h of x coordinate, we're going to do h of -3 equals, and I'm going to substitute that in. So we're going to have -3 squared plus 1 over -3 minus 2. And this is going to give us, so -3 squared is going to give us 9 plus 1 over, and this should be a -3 here. So this is going to be -5. So this is going to give us 10 over -5. We're going to have our hole, this is -2. So the coordinates of the hole would be -3, -2. Right? We're going to put that on the graph as well. So we have -3, -2. And that's going to be right about there. Hopefully that's showing up. -3, -2. And then the next part, so C and D are going to be the x and y intercepts. So we're going to go with that. We'll start with the y-intercept. So for step C is going to be the y-intercept. And remember to find the y-intercept, all we're going to do is substitute a 0 in for x. And we have the function here. And we're going to substitute a 0 in for x. So we have 0 squared plus 1 over 0 minus 2. And this is going to give us a y-intercept. And this is going to be negative 1/2. So we do have a y-intercept of 0 comma negative 1/2. All right, I'm going to sketch that on the graph as well. It'll be right about here. All right? Right about there on the graph. We'll get that going. And then let's figure out if we have any x-intercepts. So that's part D. And then for the x-intercept, all we need to do is substitute a 0 in for y, or in this case, h of x. So we're going to make h of x equal to 0, and then all we need to do is the numerator of our function. So we're just going to set the numerator equal to 0. And the numerator of our function, if I just scroll right back up here again, was just x squared plus 1. We don't need the denominator. So I'm going to have 0 equals x squared plus 1. And we're going to solve this equation. And you can see here, if I subtract 1, we're going to get negative 1 equals x squared. We're going to wind up getting x equals plus or minus the square root of negative 1. And that's going to give us an imaginary number. So that's telling me that my intercepts are imaginary, and we're not going to be able to plot those on our real coordinate system here. When we solve for x and we get an imaginary answer here, this is telling us that we have no real x-intercepts. So this graph isn't going to cross the x-axis. It isn't going to intercept the x-axis. And that's really what we have so far. So we have a slant asymptote, and we have a vertical asymptote. We do have a y-intercept, and we have the existence of a hole, but no x-intercept. So our test regions are going to be a little limited on this. And normally what I like to do with the test regions is you can plot as many points as you want, as I've said in the other videos, but you really only need 1 point for the most part to tell you whether the graph, and again, we're looking with the test regions, we're looking to see where the points of the graph are above the x-axis or below the x-axis. And you really only need 1 point to do that, but since I really only have 2 test regions here. I have from negative infinity to 2, and then 2 to infinity. I'm going to wind up plotting a few more points in each test region to get a real good idea of this graph. So I'm going to clean up this, and I will be back with the test region set up and the sketch, and we'll conclude this example in this video. I'll be right back. All right, welcome to the final part of the video. This is where we're going to have our test regions and our test points and sketch the curve of the graph. So as you can see, I've got my first test region. Remember, the test regions start at negative infinity. Your first test region starts at negative infinity, and we're going to ride along the x-axis until we hit either an x-intercept or a vertical asymptote, and I stop here at 2. So my first test region, as you can see right over here, goes from negative infinity to 2. This point right here is part of the slant asymptote. That's not an x-intercept. So I can pick any point that I want in this region, and I think I'm going to do, as you can see over here, I think I'm going to do h of 1. So I'm going to substitute h of 1 into my reduced function, and we'll see what we get out of that. So we're going to have 1 squared plus 1 over x minus 2. This is going to give us a value of 2 over negative 1. That's negative 2 there. And we substituted in a 1. We got a value of negative 2 out. And you can see I have it right here on the graph. So that tells me right there that everywhere from negative infinity to 2, my points are going to be below the x-axis. And we kind of knew that already, because at 0, we get a value of negative 1/2. And also at -3, we had the hole there at -2. So that kind of tells us that this graph is going to wind up going down towards the vertical asymptote this way, and it's going to go up to the y-intercept curve and then go, towards the hole, towards the slant asymptote as it goes to -infinity. So what I think I'm going to do is I think I'm going to pick another point a little further out. We've already got one here at -3. I think I'm going to go a little further out. I think I'm going to do h of -10, and that will give us a good clue over here. Let's do h of -10. So we're going to have -10 squared plus 1 over -10 minus 2. So this is going to give us 101 over -12. So this is going to give us -8 and 5/12. All right, not a great number. We have -10 and then -8 and 5/12. So almost -8.5. So if I'm way over here on the x-axis at -10 and then 8 and 5/12, it's kind of tough. So we're kind of like right down here. And that's pretty much what we were thinking, right? As it's getting, as it's going off to -infinity, the graph is going to get really close to that line, that slant asymptote. So if I sketch what we have, the graph is going to wind up going up like this, and then it's going to go approach the hole, and it's going to get really close to that asymptote. And in this direction, it's going to wind up going down towards the vertical asymptote. So there's the sketch of that part. So now all I need to do is, figure out the behavior in here, and, we'll be done with this graph. So the next test region is going to go from, if I change the color to green, we're going to pick it up where the first test region ended. We're going to start at 2, and we're going to wind up going out to +infinity, as you can see there. And we'll be able to sketch the rest of this curve. All right, so the next test region we have is going to go from 2 to +infinity. And I think what I want to do is, again, we need to pick a point from 2 to infinity. So let's do h of 3. And we're going to have 3 squared plus 1 over 3 minus, this should be 3 minus 2. So we're going to wind up getting 10 over 1, so we have a value of 10. So we substitute it into 10, and we get a value, or substitute a value of 3, we get a value of 10. So let's plot that point on the graph. We have 310. And I think what we'll do is we'll put in, let's do h of 7. And we'll see the behavior as this goes towards +infinity. So of h of 7, this is going to give us 7 squared plus 1 over 7 minus 2. So this is going to give us 50 over 5. So again, we have a value of 10. We have the point that we're going to plot, 7, 10 is our next test point on the graph. So we get that out. It looks like the graph is going to do this. It's going to go up towards the vertical asymptote. It's going to kind of, it's going to go this way, kind of make a curve, and then go out this way. It's kind of the behavior. Let's go out just a little further. I'm going to do one more test point. Let's go h of 10. And what we have is, if I substitute a 10 in, we're going to have 10 squared plus 1 over 10 minus 2. So we're going to wind up getting 101 over 8, and this is going to give us 12 and 5/8. So we have the point 10 and 12 and 5/8. Again, these numbers aren't the best. So we're at a little bit more than 12 and a half. So let's go out on the graph, and let's pencil that in. So we're at 10 and then 12 and 5/8. That's a little tough to see on this graph. It's kind of somewhere in there, right? Because the line right above it, so this gray line right above it is 13. So, right in there would be as close as I can get it. And then we kind of understand what's going to happen here. So the graph is going to wind up, coming down this way, and it's going to go shoot out towards the asymptote this way. and then it's going to wind up riding up towards the vertical asymptote that way. So that's the behavior. That's what that graph would look like. I really have no other points or no other places on the x-axis I need to create test regions. That's the shape, and that's what it would look like with a slant asymptote. So again, hopefully you enjoyed the series on rational functions. We've covered all different types, covered all the pieces, and I will see you in the next series of videos. Take care.